Chemistry 3112, this is experiment 15.1, the stereoselective reduction of benzyl with sodium borohydride. In general chemistry, you learned that redox reactions are defined as a transfer of electrons. You might remember oil rig oxidation is losing electrons and RIG reduction is gaining electrons. But in organic chemistry, redox reactions can be thought of oxidations being a net loss of hydrogens or a gain of oxygen atoms. And reductions can be thought of in the opposite way, that reductions are usually a gain of hydrogens or a loss of oxygen atoms. And here we have showing, for example, a carboxylic acid. So down here we have a carboxylic acid, and we see the oxidation state of the carbon there is +3. And then it gets reduced to an aldehyde. How do we know that? Well, first of all, we can see that we are losing an oxygen. When we go from the carboxylic acid to the aldehyde, we're losing an oxygen atom. And also we're changing the oxidation number, right? It's going from +3 to +1, and so it's gaining electrons, and therefore it's being reduced. If we take that aldehyde where the carbon has an oxidation state of +1, we can reduce that aldehyde to a primary alcohol that's shown here. There's a hydrogen atom that's left out, but we know it's there. Anyhow, when we reduce that, we take the oxidation state of the carbon from +1 to -1. And so this is a reduction. Why? Because we're adding hydrogens, but we can also look at it in terms of the oxidation state of the carbon, and we can see that we are gaining electrons, so overall it's being reduced. Now, if you don't remember how to calculate the oxidation state of a carbon, we imagine the electrons in a bond as a lone pair on the more electronegative atom. Now, when we calculated formal charges, this is something that you learn how to do in general chemistry. We say that formal charge is the number of valence electrons subtract the number of bonds and the number of unpaired electrons. And so you treat the bonds as though they're broken homolytically. And so here we would have 4 valence electrons for our carbon, subtract 4 unpaired electrons, and that gives you a charge of 0, a formal charge of 0. Whereas when we look at the oxidation state of carbon in this molecule, methanol, we break these bonds heterolytically. That is to say that we give the electrons to the more electronegative element in the bond. And between a carbon and a hydrogen, the more electronegative element is a carbon. And that's why the carbon takes all the pairs of electrons from the carbon-hydrogen bonds. But oxygen is more electronegative than carbon. And so it takes the electrons in the carbon-oxygen bond. So if we calculate the oxidation state of carbon here, it's going to be 4 minus 6, which gives us -2. And so you can see that oxidation states of carbon can range all the way from -4 to +4. We have methane, which has an oxidation state of -4, and we can go all the way to something like carbon dioxide, which has an oxidation state of +4. So again, just like in general chemistry when we talked about oil rig, in an oxidation reaction, the carbon's oxidation state is going to be increased, and that's because overall we have a loss of electrons, and then a reduction reaction, the oxidation state is going to be decreased. A little bit of background in our reaction: the reduction of carbonyl compounds is an important synthetic route to alcohols, so reducing aldehydes and ketones, or carboxylic acids and esters. Now, as far as aldehydes and ketones go, they can be reduced by a variety of reagents to yield their respective alcohol products. If we reduce an aldehyde, we produce a primary alcohol, and if we reduce a ketone, we produce a secondary alcohol. Now, the ways that we can do that is we can use high pressure hydrogenation. So this is the conditions you might be familiar with: hydrogen and a catalyst like palladium, platinum, or nickel. And again, we have to have hydrogen gas, and so you can see why that might not be good to use at the undergraduate level. Or we can use a metal hydride transfer reaction. And the metal hydride transfer reagents that you're probably familiar with are lithium aluminum hydride and sodium borohydride. Those both come up in Chemistry 3111. And so this lab is going to focus on the reduction of ketones to alcohols. Namely that we're going to start with a molecule called benzyl, which has 2 carbonyls or 2 ketone functionalities, and we're going to convert it into hydrobenzoin. Sometimes I call it hydrobenzoin, but I'll try to stick with hydrobenzoin. Anyhow, the most useful reagents are the complex metal hydrides. Again, lithium aluminum hydride, which we abbreviate as LAH a lot of times, or sodium borohydride. Both of these are very good reducing reagents. And lithium aluminum hydride is the stronger of the two. It reduces aldehydes, ketones, esters, carboxylic acids. But the problem is it's pretty reactive. It can react violently with water and other product solvents like methanol or ethanol. And so again, you can see why this would not be good to use at the undergraduate level, whereas sodium borohydride is a good reducing reagent, but it's weaker. It doesn't react violently with product solvents, and it only reduces aldehydes and ketones. So you can see how it's going to be a good choice to reduce benzyl, which contains 2 ketones. Sodium borohydride is nothing more than a white solid. Here's a bottle of sodium borohydride. It's safe to use. It can be weighed out on a balance effectively. It's a very selective reducing agent in that it's only going to reduce the carbonyl. It's easy to weigh out on the balance, as I said, and you have to cap it after use because it is hygroscopic, meaning that it absorbs water or moisture from the air, and that will destroy it. So you want to make sure it's capped at all times. The mechanism of sodium borohydride is rather complex, but a simplified version is shown here on this slide, and this version suffices for our class. Sodium borohydride is the source of the hydride ion, which does a nucleophilic addition to the carbonyl, and then followed by a proton transfer from the solvent. So the first hydrogen in the reduction comes from the borohydride reducing agent, and then the second hydrogen actually comes from the solvent. Here's our starting material, benzyl, and you can see that it has 2 ketones in it. Now we're going to treat that with sodium borohydride, and so there's several possible products that we could get. If we reduced only one of the carbonyls, the hydride could attack from either face of the molecule, and we could end up with this molecule called benzoin, and that would be racemic because, again, the hydride could attack from either face of the molecule. So that's one option. And as far as the reduction of both carbonyls go, we could either reduce both of them to end up with the meso product, or we could end up with an enantiomeric mixture of 1S2S and 1R2R hydrobenzoin. Now keep in mind that in the 2 enantiomers that I have here with this red sign next to them, they are going to be diastereomeric to the meso product. Now if you're confused as to why you can end up with so many possible products, remember that a carbonyl is planar, right? The carbon in a ketone is sp2 hybridized, and so this carbon is sp2, and so it has trigonal planar molecular geometry. Therefore, again, we could end up with the racemic benzoin product, because the hydride can attack the carbonyl from above or below the plane of the molecule. Therefore, you can have different stereoisomers from the attack on that benzoin. And hydrobenzoin has 2 chiral centers. So there's a possibility of either forming the meso compound or a pair of enantiomers. And what you need to do is to determine which products are formed during the reduction of benzyl. Are you ending up with the racemic benzoin, this compound? Are you ending up with enantiomeric hydrobenzoin, so a mixture of these 2 enantiomers, which are going to have the same physical properties, so that's why they have the same melting points? Or are you going to end up with the diastereomer of the enantiomeric hydrobenzoin, which would be the meso hydrobenzoin? And so the way that you're going to determine which product is formed, you're going to take a melting point of your product, and you're also going to take a TLC. An IR will be provided on the data sheet. Using the melting point, the RF from the TLC, and the IR, you should be able to identify the final product. In terms of stoichiometry for this reaction, remember each mole of sodium borohydride can provide 4 moles of hydride, right? Because if we draw the Lewis structure of the borohydride, you can see that boron is attached to 4 hydrogens. So again, it provides 4 moles of hydride. That's why for every 2 moles of benzyl, we only need 1 mole of sodium borohydride to produce 2 moles of the hydrobenzoin. Next, we'll talk about preparing for the pre-lab and some of the laboratory instructions. The first thing that you'll want to do is read the background, which is experiment 15.1a, and you want to review the following techniques. we want to make sure that you understand how to take a melting point, a TLC, how to do a filtration, and how to properly mass in the laboratory. I can't stress this enough. If you're unsure about any of these techniques, be sure to take a look at them. They are all covered in the lab manual. When you prepare your notebook, make sure to put in a header with your name, date, the title of the experiment, the purpose. In the purpose, you want to answer these questions. What are you making and what are you starting with to make it from? How are you going to isolate the product and how are you going to purify the product? And finally, what I think is even the most important is how are you going to characterize the product? Characterizing means how are you proving the product? How are you proving what the actual structure of that product is? Next, you're going to have a table of reagents. Be sure to include all organics in addition to their usual names and structures, molecular weights, boiling and melting points, and other physical properties. Be sure to include all possible products in the table of reagents, and you don't need to include water. Don't forget to include the TLC solvents as well. After your table of reagents, be sure to include all of the same compounds in the safety table. Next, you put a balanced chemical reaction. No need to include the mechanism, but there are multiple products possible due to stereochemistry, and all of these products have to be included. Next, you're going to include a theoretical yield and limiting reactant calculation. Then, for your procedure, be sure to use the 2-column format. That means you split the page down the middle vertically, and you want to see page 366 in the lab manual for the procedure. When you mass your benzyl, you're going to mass around 200 milligrams. If it's anywhere between 190 and 210 milligrams of benzyl, you're totally fine. Use a 25 ml Erlenmeyer flasks instead of a 10 ml, and add 2 mils of 95% ethanol and swirl it around. If after 5 minutes all of your benzyl hasn't dissolved, go ahead and just start with the addition of the sodium borohydride. You can see that the reading on the balance here is 0.199 grams. That is equal to 199 milligrams. So you can see that that falls in the range of 200 milligrams plus or minus 10 milligrams. You're going to mass out 90 milligrams plus or minus 10 of your sodium borohydride. That's if the bottle is new. If the bottle is old, you're going to need a little bit more because some of that sodium borohydride will probably have absorbed some water, rendering it inactive, and so you'll need to have somewhere between 100 and 120 milligrams. Your instructor is going to notify you exactly which mass to use. But for writing out your procedure, just say 90 milligrams. Now this is one case where you're going to be asked to use whey paper on the balance, and you're going to have to be very careful with it. Also, it's best to keep the sodium borohydride on the table as opposed to the hood because the fume hoods have a strong vacuum for their ventilation, and sometimes whey papers can get sucked up into the fume hood. I know this from personal experience. Also, you can see the balance here reads 0.088 grams. That is 88 milligrams. And so you can see that that falls in the range of 90 plus or minus 10 milligrams. The benzyl has a yellow color to it. These are some pictures of the sodium borohydride addition. You can see that there's some bubbles being formed. I know the pictures are a little bit fuzzy. After you've added the water, you're going to heat the solution to boiling, and at this point the solution should be clear and colorless. If there are any insoluble impurities, you're going to filter them off using a filter pipette. The procedure for how to use a microscale filter pipette can be found on page 44 in the lab manual. We expect you to look at this before coming to the lab. After you've transferred the hot clear solution to a clean Erlenmeyer flask using a filter pipette, you're going to add an additional 2 milliliters of hot water and allow the solution to crystallize undisturbed to form shiny, thin plates. When you're waiting for the crystals to form, you want to be patient. It can take up to 30 minutes to have the crystals form. Once the crystals have formed, you're going to want to cool the crystals in an ice bath to force more of them out of the solution, and then you're going to filter them off using a Hirsch funnel. You're going to wash the crystals with a minimum amount of cold water, let them dry, and then finally weigh the product. You can see that the yellow color of the benzyl is gone, and our product is a white solid. The TLC will be run using a mixture of 9:1 methylene chloride or dichloromethane to ethyl acetate. That means you're going to take 9 milliliters of dichloromethane and 1 milliliter of ethyl acetate in your 10 mil graduated cylinder, and you're going to put that in your developing chamber. On the TLC plate, you're going to spot benzyl, mesohydrobenzoin, racemic hydrobenzoin, and racemic benzoin. We're going to have those solutions already prepared for you. Then you're going to take about 3 milligrams or the end of a spatula of your product, dissolve it in a little bit of ethyl acetate, around 5 or 6 drops. Do this in your crystallization dish, and then you're going to spot that on the TLC as well. Your instructor will tell you the order that they want the spots to be on the TLC plate. It's always a good idea to put your product somewhere in the middle. Even though you've written down the masses in your procedures, remember to record the actual masses that you used, and you need to use those in order to recalculate the limiting reactant and the theoretical yield. Also, be sure to record all observations, particularly anything that you don't expect, and any changes to procedures. When you get home, be sure to complete the data sheet. Remember that calculations, sig figs, annotation, and the summary is all very important. All of it matters in determining your final grade. Some reminders: the TLC is done in the lab. Don't forget to save some product for the TLC. The crude is not recrystallized. A melting point will be obtained, and since water is your solvent, you may or may not be able to get your product dry enough for the melting point to be done on the day of the lab. You might have to return a couple days later to complete it. Again, your instructor will provide more information about this in the lab. As always, you don't have to run the actual IR on your product. We provide the IR in the data sheet. And you can write in your summary as if that IR was run by you. You can say, my IR, I see these signals and these signals are gone, or whatever. Remember to annotate the IR completely. This means that functional groups have to be found in the IR and annotated. On your sample vial, be sure to put the label with your name, the section number, and the product or the name of the experiment, and we will grade your product quality and the yield.